Introduce yourself, get ready for clapping, go.
I'm Marcin Szczepanski, and I'm talking to you today about JavaScript debugging the hard way. Just a preface for this talk is that this is like a 10-minute version or 10-minute part of a longer talk that I'm going to be giving at JS Congress in April in Munich. I was lucky enough to get my talk accepted. So this is like a small part of it. I'm going to kind of have to skip over some of the story aspect so I can focus on the technical stuff, which is the interesting part. But yeah, I assume that talk will be up on YouTube sometime after the conference, so keep an eye on that if you want to see the rest of the story. So yeah, by the title, you'd think this is a talk about debugging, and this version kind of is. But the long version is going to be a talk about our Webpack upgrade from Webpack 3 to Webpack 4. So how could I get a 30-minute talk out of that? Well, it was quite challenging, mainly because of problems of scale. So Jira, as you may be aware if you've ever used Jira, is quite big. There's a lot of surface area, a lot of different parts to Jira. And so while a normal Webpack upgrade, you might expect, you change a few things in your config, upgrade a few plugins or whatever, and mostly it should kind of go pretty smoothly, and that's been my experience in the past with smaller apps. With Jira, it wasn't that easy. So we had it working. We had the local sort of setup working without any optimizations, but when we tried to turn on source maps and all the stuff we use in production, it just kind of blew up. It would take hours to run if it ran at all, if it didn't run out of memory at some point. So yeah, that was our experience with that. So to explain why very quickly, so Jira is some 1.7, or Jira's front end, at least the modern front end, is some 1.7 million lines of source code. That includes tests, so that's not all the code that we end up bundling, but we end up producing 200 megabytes of assets and 200 megabytes of source maps in our Webpack build. So our Webpack build, our production one, takes like roughly about 20 minutes, which if you're working on anything smaller than Jira might seem like a long time, but that's after a lot of optimization to get it down to 20 minutes. And so this talk, I'm going to focus on the first part of our issues, which was that, like I said, when we tried to build it with source maps, build it in that production config, it just failed. So a thing I'm going to be talking about is mainly profiling JavaScript applications. And so just to explain that first, I'm going to be using this a lot. This is a flame chart. If you haven't read a flame chart before, basically time goes along the x-axis, and these are like function calls. So each bar is a function call, and for bars that are stacked on top of each other, the one below means it was called by the function above. And when you get down to like that red square area, that just means like usually that a function does a loop or something and calls a lot of functions in quick succession. So it looks a bit daunting at that point, but it's pretty, it makes sense. But we'll be looking at these a bit, so I thought I'd just explain that for people who haven't necessarily worked with these before. So the normal way that you would connect your profiler or debugger to Webpack, or one way, is to run it like this. So you run Node, you tell it that you want to turn on the inspection API, and then you run Webpack. And so you could do that locally. You could connect, Chrome's got Node DevTools. You can connect that up, and then you can see what Webpack's doing. That didn't really work very well. Like I said, the build took hours to run before it failed for some reason. And so connecting a profiler, you'd end up crashing either the profiler, you'd end up crashing your process and not getting an output. So it was really, it was hard to get any local data. So I found this really useful plugin called the CPU Profile Webpack plugin. And what that does is you can install it like any other plugin in Webpack, and it uses that Node V8 API in order to generate a CPU profile from within Webpack and output it to a file. So something I missed saying is that while it failed to run locally, we could get it to sort of run in our CI environment, because the machines are much beefier there, the agents that we use for our continuous integration. And so we could add this plugin, push it up, get it CI to run it, and produce that CPU profile as an artifact, which we could then download and load into the profiler locally, which actually meant you could actually see what was happening. So before I go into our specific profile, this is roughly what a normal sort of Webpack build, at least our Webpack build, looks like. So there's a couple of different parts to it. Yours might look different because of different plugins that you run, different optimizations and things that you do. But roughly there's a couple of main parts. So the first part is bundling. So this is where Webpack reads your source files, follows the dependency tree, and generates this graph of everything. The second part, it optimizes that graph, so that's where it actually decides what goes into what bundle. And then the next three phases are actually part of one sort of thing, which is the actual optimization. So it does some work in advance to pre-generate some source map stuff. Then it minifies, and the reason there's not much activity there is because minification happens on worker threads, so it's not happening in this main process. And then it produces those final source maps, and finally the last phase is emit, which is where it actually writes everything out to disk. So in our normal build, as I said, they're roughly like 15, 20 minutes. That's sort of what the timings of those phases look like roughly 2 to 3 minutes per phase. So when I loaded the CPU profile from one of those failing builds, it looked more like this. So you can see that things have been squashed up, except for that source map section is quite large proportionately. You probably can't read the timings up there, but the way these numbers look, it's about 2.5 hours worth of source map generation. So clearly there's something wrong in that source map process. So we can zoom in on this flame chart in order to work out what is contributing to all that time. So the easiest way to do that, is that playing? Yes. So you can select like a section of the flame chart, zoom in, and you can see that there's repetitive code running over and over. And you can see there's quite often you can see this normalize and split. And that is like literally like a JavaScript split on a string. And it's taking 26.5 minutes of total time just doing string splits during this build. And you can see also there's a bit of garbage collection happening quite often, so that's pretty suspicious. So the profiler has another view you can go to, which is called like bottom up, which shows you the most expensive functions in your code. And what that showed us is that split was, 35% of the runtime was spent doing split, and map was the next one down, and that was map calling split. So clearly that was suspicious. And that chart gives you then a reference to where that was happening. So if we open up that file and search for split in it, you find this line of code. And so what this is essentially for a source map, for every line or every file, it calls this function to normalize the path. So that's split is using a regular expression to split multiple slashes into parts. But what it's doing is it's doing it over and over again, and it's creating a new regular expression every time it does it, for one. And secondly, that's not a really efficient way of splitting a string by forward slashes. And so you look at it and think, that's like an easy potential performance fix, but it doesn't take much searching to find that someone else has already fixed this in this source map library. And they've pretty much done exactly that. They've taken this path split and replaced it with just a string walk, not using regular expressions at all, and they've also added a small cache around that whole function because it quite often gets called with the same path over and over. So why, given this PR was a couple of months before I was trying this, why wasn't this already in Webpack? So this is where the fun part comes in. So source map, the library, is a library provided by Mozilla, and so Webpack uses version 0.6 of that. And that fix went into 0.7. And 0.7 also changed to like an asynchronous API. They dropped Node 6 support and a bunch of other stuff that meant Webpack couldn't bring that dependency in. Someone already requested that performance fix get backported. And that has been sitting around for a long time without any sort of comments from anyone from Mozilla. So they're not very keen, it seems. So what do we do in this case? One thing you could do is maybe fork it. So you take the source map library and you apply your fix yourself and then use that dependency. But the problem with doing this is that in this case it's a bit impractical. Source map's like a leaf dependency of a bunch of other dependencies. To do this effectively, we would need to not just fork source map, but fork Webpack sources to use that version of source map and fork Webpack to use that version of Webpack sources. And so you end up having to maintain all these forks, and it makes it really hard to upgrade. It's not really practical. So another cool tool that I found is something called patch package. And so what this tool lets you do is you go into node modules, you go into that source map dependency, and you apply whatever changes you want. And then you run patch package for that dependency. And what it will do is it will download the original dependency from the registry, do a diff, and create a patch file in your repository. And the second part of it is you run patch package in post install, and it then applies that patch after your node modules have installed. So it means you can apply these patches without waiting for an upstream library to be released in a case like this where it's hard to do anything else about it. It's also useful for if you want to raise a pull request against an open source project, but you want to use the fix in the meantime in an easy way, you can use something like patch package to use your patch before it gets accepted by the maintainers. So anyway, that patch improved things a lot. That's basically totally unblocked most of the rest of our upgrade. Things were running again in the normal amount of time. Well, 18-ish minutes, like 15 to 20 minutes. That's considered normal for our builds at the moment. One interesting fact though as well, I was trying to generate like those traces again for this, because this all happened like 6 months ago. I was running with Node 12, and it seems in Node 12 that performance problem with the original source map doesn't seem to exist to as much of an extent anymore. When you do like a profile, you don't see that split come up in like the top, executed code. And you can see that, so Node's doing something different with regular expressions that get created and called over and over again. It actually fixes that for you by just upgrading. So yeah, that's pretty much it. The key takeaways from this part of the talk, at least, is really helps to understand like your tools that you've got available, especially debugging tools like profilers and stuff. They might seem scary, but there's actually it's pretty easy to sort of get around, and you can really easily identify these like hotspots by just going into it. And you can sometimes they just show up really clearly. Sometimes it takes a bit more work. Find others with your problem, like probably someone else has run into this, especially if it's something to do with open source. There might be a good reason why it hasn't been fixed. There might be a semi-good reason, like in this case, why it hasn't been fixed yet. And lastly, if you upgrade your dependencies, like if we'd have upgraded to Node 12 before Webpack 4, we might not have noticed this. We might just, the build's like a couple of minutes slower and spend a whole lot longer trying to work out what was wrong. And that's it. Thank you.
Thank you.